Okay, there are many philosophies on teaching trig, like the order you're supposed to teach it. But a lot of the pre-calc books agree that we start with the unit circle approach, and then we go from there into triangles. You won't actually see many triangles in chapter 5. You won't see triangles until you get to like chapter 7, long after you've started trigonometry, the study of triangles. You finally see them much later. But everything is based on the basic rule SOHCAHTOA. You guys remember SOHCAHTOA? Sine is the opposite leg divided by the hypotenuse. Cosine is the adjacent leg divided by the hypotenuse. Tangent is the ratio of the two legs, opposite over adjacent. So it is based on that in part. But you couldn't tell from reading this. What in the world? Go ahead and draw this picture real quick and write these rules. Okay, so you've always thought of sine, cosine, and tangent as SOHCAHTOA, right, probably? And that's just, like I said, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. But we're not drawing a triangle here. Like, this just looks like a circle, and then there's all this y, x stuff going on. Like, what is that all about? Maybe you also don't recognize these symbols down here, cosecant, secant, and cotangent. But if you look closely, these three really are just the reciprocals of sine, cosine, and tangent. See? Notice that cosecant down here is just 1 over y, and sine is just y, see? And same thing with cosine and secant. They're just reciprocals. And then cotangent is just the reciprocal of tangent. Okay? So that's not really that mysterious. If you know the 3 blue ones, then you can figure out the 3 red ones. The only hard part then is to remember which names are which. But there really are just 3 reciprocals. Okay? So what does this have to do with triangles? Well, here's the basic idea. Let's say that you pick any random point on the circle, okay? And just so you know, we always start here. This is called the initial ray. We always make the initial ray the positive x-axis. The positive x-axis. So we always start here, and we call this basically 0 degrees. It's just a convention. I don't know why we picked the positive x-axis to be 0. We could have picked the positive y-axis to be 0. Like we could have put the 0 up here like we have on compasses, for example. When you're traveling the globe, you usually use north as 0. But we chose to use the right-hand side there. And then as you go around the circle, like this, okay, as you go this direction, that's considered the positive direction. And if you go the other direction, that's considered the negative direction. So it's interesting, but clockwise, going the direction of a clock is considered negative. That's really interesting. Okay, so you don't have to draw everything I draw because your pictures will get really cluttered. But you need to indicate that this direction is positive and this direction is negative, even though that's the direction a clock would turn, right, clockwise. So this is called clockwise, CW, and this is called counterclockwise, or CCW. So CW means clockwise, if you want to make a note of that. Okay, so I'm going to clean up my drawing. I really don't want to have everything on one picture. So take those directions off. I just wrote them at the top of the page there. They're right here still. Okay, and then if you were to go on a circle, traveling around the edge, you are traveling along an arc. We called this an arc yesterday, right? And we said yesterday that if you travel a certain distance, let's say, I don't know, S, along this circle, if you're studying radians, if you're using radians, and you multiply r times theta, that gives you s. So we had said that r equals s equals r theta. Remember that rule from yesterday? S equals r theta. But the radius of this circle is what? Look at the given right here. The radius is 1. This is why we call it a unit circle, by the way. UN is the prefix 1, right? Uni. Unicycle. Unity, right? Even the Spanish word uno means 1. Unit always means 1 of something. The unit price is the price of 1 ounce of shampoo or whatever. So maybe you've heard the word unit used, but you never realized that actually means 1. That's what it means. Okay, so this is a radius of 1 circle. In other words, S is theta. This is really, really important. What I'm saying is, on this particular circle, because the radius is 1, the arc length is the angle measure. Okay? All right. So, when you draw an arc of sorts, let's say the one I've drawn, right? You get a central angle, and there's a radius, and there's an S. But S and the central angle are equal if the radius is 1. The other thing that happens when you draw an arc like this is you find yourself at a point. So if you're going to travel around the circle like this, you're going to find yourself at a specific coordinate point. That point will be x comma y. So this brings up an interesting question. What's going through my mind is this. If the coordinates are x and y, what does that have anything to do with the angle theta? Okay, how would you relate the xy distances, you know, the x coordinate and the y coordinate? What does this have anything to do with that theta? You see what I mean? Now, if you wanted me to go to point P, so let's call this point P, you said, Mr. Shore, I want you to travel from point A, that's the starting point right here. I want you to travel to point P. I'd say, okay, how far is it? Just tell me how far to go. So you say, oh, I want you to go, you know, 0.7. So I travel 0.7 along that curve, and I end up at point P. When I get there, I have coordinates, right? I should be able to predict my coordinates based on how far I walked. That's a little bit complicated. I walked along a curved path, and I ended up wanting to measure 2 straight segments. See? But fortunately, what we see here is there's a right triangle that just popped up. You guys obviously see the right triangle there, right? And if you look closely at that right triangle, since the radius of this circle was, what? 1, the hypotenuse is 1, and x and y are simply the legs. So what is the connection between x and y and theta and r and all of these different things? SOHCAHTOA. SOHCAHTOA. Sine of theta is opposite leg. So I'm pointing to theta right now. It's right there, the origin. What is the opposite leg? Look at the triangle. Is it 1, x, or y? Come on, guys, look at the angle. I just marked it. It's right here. The opposite leg is y, and the hypotenuse is 1. And so opposite of hypotenuse is y over 1, also known as y. So sine theta is y. Okay? Let's do adjacent of hypotenuse. The adjacent leg is x. The hypotenuse is 1, and adjacent of hypotenuse is x over 1, which is x. So we see that cosine of theta is x. See? So this is starting to make more sense up here. And tangent is just y over x. It's just opposite leg divided by adjacent leg. Notice that has nothing to do with the y. Okay, so these three are SOHCAHTOA for a circle with radius 1. So why don't we just do SOHCAHTOA instead of this? Here's the reason. If we were to go past 90 degrees, okay, imagine we were to go past 90 degrees, If you go past 90 degrees, something interesting happens. Let's say you told me you wanted me to travel a little further along the circle, right? Well, I'm going to end up here. Did I travel a specific angle? In other words, do I have a central angle for this arc? Yes or no? Is there a central angle for this arc? Absolutely. Definitely is a central angle. Do I have an XY coordinate pair when I reach my destination? Absolutely. Anywhere you plot a point on an XY grid has coordinate pair. Right? Is there a triangle? See the problem? We lost our triangle. Where's the right triangle with theta? It's gone. You can't draw a right triangle. We've got 90 degrees in a right triangle. Plus there's this obtuse angle right here. We got too many degrees. I can't seem to draw the triangle. We'll find out later that we're actually going to draw it over here. But listen, does that black triangle I just drew contain the angle theta? No. So things look a little different in this perspective. This is why we don't want to think about SOHCAHTOA. Because SOHCAHTOA limits us to acute angles. What does acute mean?
Less than 90.
Less than 90. Nothing outside of that makes any sense unless we reconstruct the triangle on the left side. But if we use these definitions up here, there's no mention of triangles. And sine theta is y, and cosine theta is x. And it's just coordinates related to angles. No mention of a triangle. And coordinates can be negative, unlike side lengths. Okay, so this is a more versatile approach to trigonometry than SOHCAHTOA. It's sort of based on the same idea, but this allows for negative side lengths on triangles, if you want to think of it that way. It also allows us to talk about right triangles in any of the four quadrants, so we don't have to stick to less than 90 anymore. And questions like, what is sine of 91? Actually makes sense now. What is sine of 91 degrees? Why don't you guys get out your calculator? Let's find sine of 91 degrees. Just punch it in. Sine 91. What does it say? 0.105,987. Okay, press mode and put it in degrees. It's in radians right now. Okay? Sounds like. Try again. So what did you get? Say it again. What's sine 91? 0.99 what? Wow, okay, that is really, really close to what? 1. Why? Because I am saying that sine 91 is simply the y-coordinate of this point. Isn't this point like really close to 1? See how close it is to the top of the circle? The top of the circle is 1. It's a radius 1 circle. See? So no wonder sine 91 is like 0.998. It's just a hair below the tallest point on the circle. It's just barely under it. See? I wonder what the x-coordinate is. Well, let's find cos 91. Let's do cos 91. I'll bet it's something slightly negative, like barely to the left of 0. Is that true?
Yes.
What is it?
-0.0174.
Okay, so what we're saying is the coordinates of this point right here, since this is the point 0, 1, right, at the top of the circle, this point is the point negative 0.02-ish and 0.998. It's just barely to the left and below that top point. That makes perfect sense. So sine and cosine go from being this triangular thing to being a way we can calculate positions of points on a unit circle. It's a very different perspective than what you're used to. Let me ask you to find the coordinates of another point just for practice, okay? On the circle, see if you can find where 185 would be. Where do you think that is? Just put your pencil on the circumference where you think 185 would be. Remember, this was 0, and the top of the circle is 90. 91 was right here, remember? Where do you think 185 is? Go ahead and draw it on your paper. Where do you think it is? Okay, so you'll probably guess it to be right about here. Maybe even closer to the axis. Because this is 180, see? So now I'd like you to find the coordinates of that point. All you need to do is type cos 185, that'll be your x-coordinate, and type sine 185, and that'll give you your y-coordinate. So cos 185 and sine 185, those are your coordinates, write them down. You could probably even guess sort of what they are. Okay, somebody have the answer? So what did you get for x? Somebody, you can just shout it out. Negative what? 0.87? 0.087. No, that doesn't sound right. Make sure your calculator is in the degrees mode. What is cosine of 185? Negative 0.996. Okay. Oh, yeah, and I need the y value. So type sine 185. So what was it? Negative 0.087. So this is just cos 185, and this is sine 185. Does it make sense that the coordinates are negative 0.996 and negative 0.087, you said? I got my decimal in the wrong spot. This is supposed to be 0.087. Does that make sense? Well, what is the extreme left point on this circle? What are the coordinates of this point here in black? Isn't this the point negative 1, 0? Okay. And isn't this this blue point just slightly to the right of it and below it? So do these coordinates make sense to you now?
Yes.
Okay. So what are sine and cosine? They are arbitrarily chosen ratios in a right triangle, chosen by the Greeks many years ago. Or cosine and sine are the coordinates of a point on a circle with radius 1. Interesting. So we've just connected the idea of triangles to circles. Okay. Now, those angles I chose, 91 and 185, I chose those two angles for effect. Because I knew that once you saw the coordinates, you'd say, oh, that makes perfect sense. Okay? Let's do one more, and I think you'll agree it makes perfect sense, and that's at 225. So, I'm sorry, I meant 315. Let's do 315 degrees. Remember, this is 270 down here. And if you go all the way around the circle, that would be 360. So 0 degrees and 360 would be the same. It would be one full wrap around. So 315 would fall right about in here. This shouldn't take long. Type cos 315 and sine 315. Give me the coordinates. What's cos 315?
It's 0.707 and then 0.7078.
Careful. Did you type?
Negative.
The second one is negative. So why is it negative? Look at the quadrant you're in. You're in the fourth quadrant where the x-coordinate is positive and the y-coordinate is negative. Does it make sense to you that these two numbers are the same except that one's negative?
Yeah.
It makes perfect sense because technically 315 is exactly halfway between 270 and 360. See? So we've reached a point on the circle where you're the same distance from 360 as you are from 270. Another way of saying that is you are the same distance from the y-axis as you are from the x-axis. This distance is the same as this distance. It's a 45, 45, 90 triangle if you draw in a little triangle there. Okay, so this is all very very educational. We're learning that sine and cosine, actually cosine and sine, in that order, provide us the coordinates of a point on the unit circle. Okay, now the last one I picked would be considered a special angle. Special. Unlike 91 and 185, those aren't very special. What makes an angle special? So let's talk about that. An angle that is special in geometry is a multiple of 30 or a multiple of 45. Okay? So we're talking about multiples of 30 degrees and 45 degrees. For example, 0 is a special angle, technically. Why? Because 0 degrees is basically 30 degrees times 0. It is technically a multiple of 30. Did you guys know that 0 is a multiple of 30? Did you know that 0 is also a multiple of 45? Did you know that 0 is a multiple of 1,000? 0 is a multiple of any number. 30 degrees is our next largest value. It's 30 times 1. 60 is the next multiple of 30, and 90. And then we have 120, that's 4 times 30. And then we have 150, right? And then we have 180, and 210, and 240, and 270. That's basically 8 times 30 and 9 times 30. And then we have 300, that's 10 times 30. And then we have 330, that's 11 times 30. And then we have 360. These are all special angles. So is 390. So is 3,000 degrees. But we've already gone around the circle once. Okay, what are some others? Multiples of 45. 45 degrees. 90, but we kind of already listed that. 135, that's 45 times 3. Then we have 45 times 4, but that's 180. We already have that up top. 225, that's 45 times 5. 270, but that's just 45 times 6. We already have that. The next one is 315. That's new. See? 360, that's a multiple of 45, but we already have it. These are the special angles. Okay, so the ones we're going to do on this page are everything except the multiples of 90. And then on the next page we'll do the multiples of 90. The ones I'm circling are called quadrantals. Okay? This one, this one, this one, this one, this one. These ones are called the quadrantal angles. Does anyone know why we call them the quadrantal angles? What's so special about these guys? Yes?
You mark the beginning and then the end of the next quadrant. So you like it by a
Yeah, these particular angles always are on an axis, right? So if you go back to your picture, 90 degrees is the vertical y-axis, the upper y-axis. 180 is the left-hand side of the x-axis. 270 is the lower side of the y-axis. And 0 and 360 represent the right side of the x-axis. So these are special in their own way, okay? And now what I'd like to do is make a table, you may have seen it before, that contains the sine of 30 and the sine of 60 and the sine of 120 and the sine of 150 and the sine of 210, okay? And their cosines and their tangents and so forth. All right? So that's what we're going to do. It's going to take a while to make it, but then you're going to memorize it. And you'll be tested on it. If you have Miss Chen's class, you've already memorized this table at one point. Okay, the angle. And then we have the triangle. It's called the reference triangle. We'll have a little drawing in this box, so make sure that box is big enough for a drawing, please. And then we're going to have a box for sine theta, a box for cos theta, and a box for tan theta, and then one more box for the three reciprocals. So this will be for cosecant theta, secant theta, and cotangent theta. They'll just be the three reciprocals, respectively. Okay, so our first drawing is for 30 degrees. Okay, the drawing would look something like this. You've got your unit circle. You're going 30 degrees to this point. So this is just kind of a rough drawing, but it's basically like that. And the triangle we're drawing looks like this. The 30 degrees is at the origin. So I'm marking the 30 in blue. Okay, remember the radius is 1. That's because this is a unit circle. And if you follow the rules of the 30, 60, 90 triangle, the shortest leg would have to be half the hypotenuse. This is just basic geometry. It's half the hypotenuse for the shortest leg. And the medium-sized side on the triangle, that's the longer leg, will be that times root 3. So this is root 3 over 2. Remember, that means the coordinates of this point are rad 3 over 2, comma half. Therefore, cosine is rad 3 over 2. Sine is a half. Tangent will be y divided by x. So this part you kind of have to think about. What happens if you divide a half divided by rad 3 over 2? You're going to get 1 over rad 3, also known as root 3 over 3. These three will just be the reciprocals of those in that order. So 2 rad 3 over 3, and rad 3. These are the three reciprocals in that order. One more thing I'd like to do before we leave the 30-degree angle is to understand that 30 is exactly 1/6 of 180, so it can also be called pi over 6 radians. So we have studied everything there is to know about the 30-degree angle. Let's go on and look at the 45-degree angle. Okay, 45 degrees is next. By the way, that is 1/4 of 180. So you can think of it simply as pi over 4 radians. A drawing of it would look something like this. It's right smack between 0 and 90. The triangle looks something like this. The 45-degree angle is at the origin there. Remember, the hypotenuse is 1. That's because the radius is 1 for this circle. According to the 45-45-90 rule, the legs are basically the hypotenuse divided by root 2. So these are each 1 over rad 2. Or we probably should write that more properly as root 2 over 2. So the coordinates of this point up here are officially rad 2 over 2, comma, rad 2 over 2, and we're ready to start writing our 6 trig ratios. Cosine and sine are both rad 2 over 2. Tangent is the y divided by the x. Well, they're exactly the same, so the tangent comes out to 1. And the three reciprocals are rad 2, and 1. For of cosecant, secant, and cotangent of 45. All right, let's do 60. What fraction of 180 is that? 1/3 of 180, you guys agree? So we're going to write that as pi over 3 radians. Remember we said that the mathematicians kind of prefer radians? All right, so that makes the mathematician happy. Okay. 60 degrees, if you drew a drawing of that, it would look something like this. It's a little bit closer to the top of the circle. I'll draw it in blue like I've been doing. So there's your triangle. The 60-degree angle is marked at the origin there. This distance is 1, as we said. It's a unit circle. Radius never changes. Remember, on a 30, 60, 90 triangle, the shortest leg is half the hypotenuse, so that would be a half. And the longer leg is that times root 3. So it would be rad 3. Basically, it's rad 3 times half. So it's rad 3 over 2. That means the coordinates of this point at 60 degrees are officially 1/2 comma rad 3 over 2. So sine is rad 3 over 2. Cosine is a half. Tangent is the ratio of y over x, which just gives you rad 3. And the three reciprocals are 2 rad 3 over 3, comma 2, and rad 3 over 3. Already rationalized for you. Okay, now, how much further should we go? We've done 30, we've done 45, we've done 60. I told you we'd save 90 for the next page, right? The next one after that would be 120. But we don't have to think as hard anymore because we're starting to get drawings that are symmetric. We still need to draw. Okay? What fraction of 180 is that? What fraction of 180 is 120? 2/3. 2/3. So this is 2/3 pi, commonly written as 2 pi over 3. Remember, you can just multiply by pi over 180 to figure out the radians there. Okay, we're going to speed this up a little because our triangle is right here. But it's the same triangle we had in the previous drawing. It's the exact same triangle we had at 60. The only difference is this is 1, right? And this is still a half. And this is still root 3 over 2. But I wouldn't say that the coordinates at this point are 1/2 and root 3 over 2. I would say that the coordinates at this point are negative 1/2 and root 3 over 2. Why? Because I'm on the left of the y-axis. So aside from that negative, this is the exact same drawing as the previous drawing. In other words, the only thing that changed is my x-coordinate is now negative 1/2. The y-coordinate didn't even change. Now when I divide y and x, I get negative rad 3 instead of positive rad 3. Look how much it is like the previous entries on this table. It's the same triangle, right? And the three ratios are simply 2 rad 3 over 3, negative 2, and negative rad 3 over 3. It is very common from here on out for 2 of these to be negative and 1 of them to be positive. In other words, out of all 6, you'll find that 4 of them are negative from here on out. See, there's 6 numbers, 4 of them are negative. Only 2 of them are positive. Okay, next is what comes after 120. You can consult your special angles list. What is it? It's the 135. It's the third multiple of 45. Maybe you thought the 150 was next, but 3 times 45 comes before 5 times 30. So what fraction of pi is that? Now it's getting a little bit harder to figure out. Just multiply by pi over 180 real quick. This reduces to 3/4 pi, okay? All right. So this is 3/4 pi radians. The drawing looks like this. Okay. This is the case where the sides of the 2 legs are the same. So the coordinates at this point is just negative rad 2 over 2, positive rad 2 over 2. Like I said, we don't have to think as hard. This is the same triangle we had for 45. It's just over on the left now. So for sine, that's the y-coordinate. We have this. For cosine, there's the x-coordinate. For tangent, the ratio is now negative 1. And the 3 reciprocals are rad 2, negative rad 2, and negative 1. you think I'm going to finish this table for you? No, you will be finishing it yourself. Okay? Later, I'm going to have you do quadrants 3 and 4 on your own. Okay? Okay. The next one is 150. That'll be my last one, and then we'll head out to the assembly. This is 5/6 of 180. The drawing looks like this. This thing is called the reference triangle. Theta is actually over here, by the way. So this is not, theta is not in the triangle, but we've got a triangle that we're referring to. It's called the reference triangle. Refer to it. But the sides here are 1 still. This is a half. And this is a rad 3 over 2 down here in length. But the coordinates would, of course, be negative rad 3 over 2, comma, positive half for the x and y coordinates. So we end up with a half here, negative rad 3 over 2 here. The y over x ratio is negative root 3 over 3. And the 3 reciprocals are 2, negative 2 rad 3 over 3, and negative rad 3. I'm stopping here because you can use symmetry to get angles like 210 and 225 and 240, and also 300, 315, and 330. And that is something I expect you to do on the weekend. Come back and we'll see what it looks like. We'll then also do the multiples of 90. Those ones I'm saving because they're kind of special. So you